Thank you very much for coming today, Olga.
Great, thanks very much for the introduction. All right, great. Thank you. So I'll say right up front, so this is going to be sort of mostly a position talk, a little bit we'll sort of dive a little bit more into the technical part in the second part of it out of the three parts, and otherwise it's going to be more of a position discussion kind of talk, so feel free to interrupt, feel free to argue, feel free to tell me you disagree. I'm very happy to hear all of that. But we'll start by talking about sort of the intersection of this field of computer vision, which is sort of more established, kind of looking at different ways of processing images or videos, right? And the field of fairness, and specifically the field of machine learning fairness, which has been around for a while, but the two fields are now starting to come together. And we're starting to see some artifacts in our computer vision systems that may be not so great. So for example, in 2017, just sort of to ground us all with a concrete example of the kind of fairness I would talk about, it's a Face app, which is a application on your phone that creates image filters, right? So it creates photo filters where you can, do different kinds of filters, different kind of processing to the photos that you've taken. And one of the filters they had was Hotness Filter. So you can take a picture of yourself and you make yourself look hotter. Now, there's obvious issues with just that fact all by itself. But putting that aside for a second, if you look at what the Hotness filter actually did, what it did was lighten your skin tone. And they've, apologized. They said, oops, after a lot of public outcry. But the question sort of remained, right? So where did that come from? Like, why do we observe these kind of really troubling effects that are becoming more and more and more part of our world? Where does this come from? And so I argue there's sort of this cycle, right, where we have some human history and with bias and prejudice and all kinds of historical, oh, thank you so much, all kinds of historical issues that we have as a society that's making its way into large-scale data, that's making its way into the training data that's being used to train these models. The models then make decisions about our world, so they determine, there was also, another example, besides those Hotness filters, there was a beauty contest that, again, issues with that, but there was a beauty contest that was judged by AI judges, and again, AI judges preferred lighter skin tones sort of for similar reasons. So these AI models are making more and more decisions. I'm talking here, sort of the grounding example I used is the computer vision example of beauty, but of course, this is true in criminal justice systems, this is true in loan applications, this is true in resume processing, this is true in hiring, in all sorts of applications where AI models are now making decisions, which then become part of our history and our society. And so the question that we want to ask is this a fundamental issue? Or is there a way that we can stop this cycle, that we can sort of stop or halt the propagation of this kind of inequality? Can we adjust the AI design to mitigate this? And so in order to sort of ground this, right, so I'm a computer vision researcher, so let's talk specifically about computer vision systems. So the standard computer vision paradigm, right, so you have this is a strongly supervised learning setting. A lot of success in computer vision is due to the strongly supervised learning paradigm, right? So you have some training data that's been collected, that's been predominantly labeled by humans, but sometimes sort of labeled in using just web search results, sometimes labeled noisily, but there's sort of training data that's been labeled. It goes into an algorithm, and then this algorithm now extracts some common statistics from the data, and you can pass through a test image or a test example, and it will sort of spit out some information about the test image. So for example, the list of objects that are in there. And so the question concretely within this system is sort of where is the social bias? Where would it creep in? And can we mitigate it? And so the first kind of obvious answer here, right, is that it's in the training data. It's sort of bias in, bias out. Everything that comes down to training data, we should be collecting good training data. And in fact, this kind of thing was observed or sort of first stated, actually, I mean, it might be, I don't want to say this was really the first one, but this is sort of the first one in the modern era of computer vision. There was a paper that came out in CVPR 2011 by Alosha Efros and Antonio Torralba. They said, look, every data set is a bias sliced through the visual world. And they weren't talking about social bias. They were just talking about statistical bias. They were talking about imaging bias. And the way that they approach sort of this problem of data sets containing a biased representation of the world is they said, well, the way they illustrated it is they showed 3 pictures from each of the 12 commonly used object recognition data sets or sort of recognition data sets. And they said, look, if you're a researcher in this space, you can immediately recognize the data set just by looking at the pictures. And in fact, it is true. If you were a researcher at the time, 2011, working in recognition, you would be able to immediately from first 3 pictures know what data set this is. And they said, okay, so every data set is inherently going to be biased. This is going to come from the way data is collected. This is going to come from all sorts of decisions about the data set. So their solution was, we're just going to have many data sets. And so if we start talking about mitigating data set bias, the first obvious answer is, well, let's collect many data sets. And some data sets will be biased to certain genders. Some data sets will be biased to certain racial groups. But on the whole, if we... Hello. Put it right over there. So on the whole, if we sort of collect enough data sets and we do this right, this will be okay. So what's the problem with this? So first of all, collecting data sets is expensive and complicated, especially when they need to be large scale, which they do these days, right? So if you're training deep learning systems, you need massive, massive scales of data. And in fact, the more data you have, the better. I'm not going to talk about the experience of collecting ImageNet, right? But I can tell you, this is many years of PhD student time. This is a lot of money on mechanical Turing. This is a lot of decisions that you make along the way. You get criticized for every bad decision and get relatively little credit for any of the good decisions. And in fact, I'll actually make again, I said this is going to be a statement talk. So data collection research is historically much less respected than algorithmic research. So we could be collecting more and more data sets, but the reality is the PhD students who work on data, PhD students tend to not want to work on data collection because they're not going to get as much respect as building the next best deep learning model that outperforms the previous model by 2%. Data research is complicated, challenging, and less respected. So one reason why sort of the argument of we'll just go out and collect many data sets and we'll average across them will not work. The second thing is, so there is a value to having standardized data sets. So comparison of different algorithms is easier on common, well-established benchmarks. And this is actually one of the issues that exist in some of the subfields of computer vision now is that there's too many data sets. And sort of every paper evaluates on a random subset of its sort of, large N. So let's say, I don't know, 10 or 12 data sets, they evaluate it on N choose 2 or N choose 3, right? And so comparing across data sets become problematic. And so here as an example, I mean, we can take a look at the graph of like participation in the ImageNet challenge specifically. And I'm not saying that ImageNet challenge definitely has issues in the data for sure, as every data set does. But you can look at over the years, the number of entries that were submitted, right? The number of entries is growing. We can compare performance across the year. So in the blue line is classification error, top 5 classification error, and that's steadily going down. And part of the reason is because we're able to sort of compare different algorithms every year and iterate on them, and we can compare them on a common benchmark. And so collecting many different data sets, again, that sort of runs the risk of fragmenting or spreading the community and not making as much progress forward. And finally, and perhaps most importantly, so different data sets will have many of the same biases due to the constraints of the data collection problem. Because a long time ago, we figured out that it's not the best source of data, but it's the most abundant and easily accessible source of data is the web, right? So you can go, what's the quickest way to collect a large-scale data set is you scrape Flickr or you scrape Google search results, and that's how you get a data set, or YouTube if you need a video data set. The problem here is that there is multiple studies that show the distinct lack of diversity in web search images. So for example, this is a paper that came out in CHI 2015, where they looked at Google search results for terms like CEO. And it turns out that, of course, CEOs are predominantly men, that is no surprise, but the Google search results overrepresented that. So in fact, so this is a screenshot that I took a couple of months ago, and this actually looks more diverse than the kind of examples that they use, because back when they did in 2015, there were literally no women CEOs on the first page of the search results, and in fact, no CEOs of color. It was all white men in suits. And again, yes, that is the majority, but it is not enough of a majority to justify that the entire first page of the results would show only white men. So now, for the term CEO, things have gotten slightly better because obviously all the search engines read the paper and were like, oh my God, oh no, and went in and sort of added some heuristics to try to balance it out. But overall, this is still true that there's studies being done now as well that there's overrepresentation in the search results of specific groups. And the second thing is, so that we don't just talk about sort of race and gender bias, even though that's what's commonly studied, because that's arguably the easiest sort of diversity criterion to quantify. There's the most sort of annotated data on these kinds of attributes. But we can also look at, for example, geographic diversity. So this is a paper that came out in NeurIP's workshop in 2017. And they say that, look, they look at the geographic diversity of ImageNet and OpenImages, which are the two biggest and sort of most used image recognition data sets now. And they plot on a world map, sort of a dot for every image because the images by and large come with meta information, with GPS coordinates and things like that. And it turns out, sort of not surprisingly, these images were all scraped from web search results, and these images come from countries that predominantly upload photos to the web. These images come from countries where people tend to search the web and thus want to find these kinds of results, thus these results tend to propagate up. And so even if you sort of say, look, I'm going to collect the biggest data set I can, which is a data set of all of the images I can scrape off the web, and this is going to be many, many millions, the reality is it is still not going to be representative of the world at large. And maybe you don't make those claims. Maybe you say this is a data set that represents the US population or the appearance of these objects in the US, but those are not the claims that are being made. The claims that are being made are that this is a representative sample and that this is a computer vision system that recognizes objects, and objects are arguably sort of are universal, but that's just ends up being not true. And so again, so collecting data sets is expensive, right? The comparison of different algorithms is easier on common benchmarks, and then different data sets will have many of the same biases due to the data collection process. And so option 2 is we can have one great debiased data set, and that's what frequently people converge to. But okay, so first of all, is this even possible? So for all of the reasons listed above, so for example, that it will have inevitably, almost inevitably, the biases that come from the web search results. But this has been proposed, and this does work in some circumstances and in some domains. So last year there was a paper that came out. This was published in the Fairness, Accountability, and Transparency Conference, but also appeared in various news outlets, including the New York Times. That says, look, facial recognition technology is accurate if you're a white guy. And so they looked at gender classification on a variety of industrial deployed gender classifiers, and turned out that on faces with lighter skin tones, you have 0.7% error, and faces with darker skin tones, you get something up to 13% error in some cases. And this is a specific instantiation of a specific classifier, but they showed this holds true across a variety of classifiers. And so they said, look, well, why is this? The standard phase data sets tend to be predominantly white and light skin. So the standard phase data sets that these models are likely used to be likely used for training are predominantly light skin. And so they proposed a new data set for it's called Pilot Parliament's benchmark data set, where they actually have fair representation of people of different skin tones. And this was a really great idea because this allows evaluation of the models at test time across a variety of skin tones. So this sort of shifts the evaluation metric from being, can you recognize the faces that are overrepresented in the training set, to now at test time you sort of care equally about different genders and different skin tones. This is a great solution in this one particular case, but in general, artificially balancing the data isn't sustainable at scale, first of all, or fair. Because the reality is that if we collect a data set of computer scientists, 85% of them will be men. And you can go out and try to sample more pictures of women, but the reality is, look, this is just where we are right now. As you start thinking about, non-controversial topics like scene classification or object recognition or semantic segmentation, you already know that there will be inherently an overrepresentation of some concepts and an underrepresentation of others. If you think about, again, sort of non-controversial cases like autonomous driving, you're building an autonomous vehicle, you really care about being able to recognize all of the dangerous scenarios. Those dangerous scenarios are in the minority. For every dangerous scenario that you sort of get in your training data, you will get hundreds, if not thousands, of non-dangerous scenarios. So what do? I mean, you could oversample, but the reality is you would be throwing away data. And so at the end of the day, the data sort of comes in the way it comes in. And the question now is, what can we do with that data? So coming back to our outline side, so I would argue that without a doubt, so lots can be done on the data set side, and I'm not at all saying that we shouldn't be going out and collecting better data sets. In fact, there's a project going on in my lab now around sort of thinking through what kind of decisions we need to be making, how do we collect data sets in an ethical and in a responsible way, what kind of things computer vision researchers should be considering when building data sets. But it's not going to be the full answer, because the full answer has to somehow come on the algorithmic side of how algorithms will deal with imbalanced data. Pause here for a second in case there are questions. All right, sounds good. So algorithms will have to learn with imbalanced data. And we actually, one of the sort of troubling or most important findings in this space, this was articulated very well in a paper at EMNLP last year, which was the best, sorry, not last year now, 2017, so 2 years ago, which was the best paper award that said, look, models can amplify data bias. So it's not just that models mimic the data bias, but they will actually amplify it. And the example that they use is pictures of people doing different activities, and they're labeled with the person's gender as well as the activity that they're performing. And I forget the exact numbers, but it was something to the tune of, at training time, of the cooking images, 60% of them were women. And then at test time, you would expect that on on images, sorry, I always get this wrong, but hold on, give me a second. So it's the proportion of the proportion of images that were recognized as cooking, the fraction of women in those images was much higher than 60%. So the model had learned the correlation between gender and activity, and anytime it saw a picture of a woman, the probability that this is a cooking image, that this is a picture of cooking, went up. And so out of all of the pictures of cooking, the person was predicted as being a woman many more times, sort of more frequently than you would expect. And I think this is true. So this is true both ways, right? So out of the times that it predicted cooking, a larger fraction of those were predicted as women, and out of the women images, a larger fraction was predicted as cooking than you would expect. And so there's a lot of work on how to mitigate this. So this paper was one example of sort of how to mitigate these kinds of biases, these kinds of issues. There's a lot of work on translating different fairness constraints into models. So this is another paper that came out last year around sort of how do you there's different notions of fairness, there's different notions depending on sort of, you might care about equal error rates across different groups, you might care about sort of different, you might care about your predictor being sort of fair across different groups, and there's a variety of mathematical definitions for that. And so there's work around how do you translate these constraints into machine learning models. But I will say, so this is not a criticism of this line of work, but a lot of it is done on linear models. So a lot of it is done, that starts sort of with the premise of assuming we have a linear classifier, let's talk about what we can do and let's derive some theoretical guarantees. And I think that's a totally reasonable place to start. Because of course, these are complicated problems, starting with simpler models makes sense. But in practice, we don't actually have linear models, right? So we're talking about computer vision systems that it's a giant deep learning CNN. a lot of the things that you might learn from linear models don't necessarily generalize. And so this is the part where I'll go a little bit more technically, but not too technically, into a project that we're working on now around basically trying to simplify this bias problem to kind of its core, one version of the bias problem to its core, but the simplification is not going to be done on the architecture, it's going to be done on the sort of data and formulation side. And so to set this up, so recall this cooking example. So you have a data set, you have many pictures of women cooking and very few pictures of men cooking. And suppose you're trying to classify cooking versus driving. And so in driving, the reverse is true. You have many pictures of men and a few pictures of women. And so suppose your task is to actually use this entire data set, but your goal is to only classify pictures of women. So the question is, like, what do you do with the other pictures of men? Like, do you throw them out? But then you don't really have that much data from just the women. What do you do with pictures of this other domain? And so to sort of formulate this more concretely, so this is essentially learning a classifier in the context where you have some correlation with your target output. This correlation is a spurious correlation that you would want to avoid. So you don't want this classifier to be learning the gender correlation, because at test time you're just going to want to focus on classifying one domain. So to do this, we did a very toy illustration on, toy illustration? My computer froze. That's not great. Hold on. Toy illustration. It does not want to go to the next slide. Toy illustration. Yeah, there we go. I just did not like this one transition. Okay, so we did a toy illustration on CFAR10, which is a very simple data set of 32 by 32 images, classifying images into one of 10 object classes. And we said, okay, suppose our goal is to classify color images, but we're going to consider two options. So option one is we're going to consider what happens if we train them with grayscale only images. So now this is examples coming out of a different domain. And training option two is that we're going to have examples coming from both color and grayscale domain, but there's going to be a skewed distribution. So let's pause here, because this is going to be the sort of the running example, the place where we're going to do all of the sort of algorithmic work before we do a little bit of a transition to the real world. But so what is going on here, right? So you can imagine the color and grayscale being proxies for the two different protected attributes. You can imagine they're proxies for gender, for men and women. You can imagine they're proxies for race. The beauty of doing this in this way is that we know that there is a transformation between one domain to the other, and we know that all things are the same between this distribution of images, except for this one dimension, which is really sort of how much color you include. And so what happens here? So what happens when you actually train this model? At test time, you only care about classifying color images into one of 10 categories. What happens when you train it on one domain versus the other? So how many of you think that training option one will get higher accuracy on this test task? Some hands. How many of you think option two will get higher accuracy? Right. So it turns out that option one gets significantly higher accuracy if you train it in a straightforward way. You train a softmax classifier. Why is this? Because training option two will learn to associate the existence of color with a particular class. So training option two will, this is not true all the time, because obviously you still get 90% accuracy, but predominantly it will prefer to classify at test time, because it sees color. It will prefer to classify them into the one of 5 groups that were predominantly color at training time. And this effect will dominate whatever sort of other cues it will have learned about the low-level image statistics, or the edges, or whatever. It'll say, okay, look, I learned the simplest possible cue. The simplest possible cue was color. I learned that, so now at test time, I'm going to rely on that more heavily. And so this was, kind of surprising to us when we first saw it. But I think what was more surprising, we said, okay, great. We're going to do you guys know the story about how computer vision started as a summer project at MIT. You guys know this story? Like the field of computer vision started as basically one summer project at MIT. They had an AI lab and they said, well, we're going to do, we're going to solve this computer vision thing. Let's hire some undergrads and do it as a summer project. And then it grew into this whole field. So we said, okay, we see this problem. We're going to do, a couple of months on this to try to figure out how we train a classifier to ignore this color classification and then move on to real world things. And this turned out to be a much longer and more intricate process that revealed a lot of sort of interesting things about these models. So the question that we ask is, how can we teach a deep learning classifier to ignore this known spurious correlation in the data? So again, at test time, we're trying to classify the images into 1 of 10 object classes. We can actually, so in practice, we actually average this across color domains and grayscale domains, but we say, okay, we will have equal representation of those domains, and at training time, we have this skewed distribution. And this is work done by Clint Nami, who's my PhD student at Princeton. All right, so let's sort of start with kind of the obvious basic things, and we're gonna keep this on the left, this sort of running set of goals and running set of results, so we kind of remember where we are. And on the right, we'll talk about what are the different obvious methods we could use to do this. So again, so the goal is to teach a deep learning classifier to ignore this known spurious correlation in the data. We assume that the data is fully annotated, so it's annotated with all of the protected attributes and fully annotated with the target classes that we're trying to classify. The training is, again, so it's CFAR10, but it's a skewed color grayscale distribution where the proportion of color in is correlated with the object class. Architecture is ResNet 18. At test time, we're going to have equal color grayscale distribution within classes. So basically, any model that learns this correlation will be penalized at test time. And the metric is going to be thus mean per class per domain accuracy in percent. All right. So we're going to talk about 5 different types of results. There's actually six numbers, but 5 types of results. So the first, and I did sort of very simple illustrations here to make sure that we're sort of all on the same page, regardless of kind of how much deep learning background or not. We have this sort of a simplified version of this. This is ACNN, but you can think of it as some feature representation followed by a fully connected linear layer, followed by an n-way softmax classifier. So this is sort of the standard baseline trained in the standard way. So xi is image I, yi is the object class for image I, and then n equals 10, which is the number of classes. So this is our baseline, so this will have accuracy 88.5 and plus or minus 0.5 just to sort of help establish statistical significance. So what's the first and simplest thing you can do here, right? So the first thing that comes to mind, arguably, is oversampling. So at training time, you can oversample the images coming out of the domains that are underrepresented. So for example, if you have a class where 95% of its images are in color and 5% are in grayscale, you can just take those 5% and you can sample them 20 more times. So you can train a model with this the same way, and you get actually surprisingly here same accuracy as you did before. So this is not intuitive because you would actually expect accuracy to go up. The reason why is because you actually minimize, so training loss is actually 0 in CFAR. So this data set, this model that we're using is rich enough such that the loss is 0, and thus oversampling basically does not do much. Also point out, so this only holds if you assume the same number of epochs between the two models. If you do the same number of gradient updates, so if you do the same number of batches, so obviously with oversampling, you now have more more batches per epoch. So this holds if you have the same number of epochs and it both converge. If you have the same number of batches, it's actually oversampling actually does worse than the baseline because you end up seeing more of the sort of one-off rare examples, and that actually skews training. It takes sort of longer to recover from that. So these are the kind of 2 basic options that we could do. And so the next 2 results are coming from adversarial training, which is the current sort of best or proposed approach to doing this. And the adversarial training says, okay, I want to build a model that can classify these object classes, but not be able to classify the domains. And there's a couple of different formulations, so we tried them both. So one formulation came out of ECCV workshop in 2016, but it's actually based on some work that was published, I think, in ICCV 2015. So it says, okay, we're just going to have a CNN that's classifying the image. We're going to have the n-way softmax that's classifying the objects. We're also going to have a d-way softmax classifier that's classifying the domain. And then we're going to have essentially two alternating loss functions. So one that we're going to use to basically train this d-way softmax. So that's going to train this gender classifier, train this color grayscale classifier, which, by the way, can be trained very well in this domain, as you can imagine. So color grayscale is easy to classify. And then we're going to have a loss that basically says, okay, but once the classifier is trained, so now we're going to encourage the n-way softmax classifier that's classifying the object classes. We're going to encourage it to be able to predict the object classes well, but actually have a uniform distribution across the domains. And so what this is intuitively going to do is basically say, okay, I want to learn a representation that's discriminative for the object classes, but not discriminative for the domain. So I want to learn a FC7, the last sort of fully connected layer of representation, that's not going to allow me to classify color grayscale images, but it will allow me to classify the target classes. So what happens when you do this is that you get much lower accuracy. I'll show you a visualization for why this is in a second, but intuitively this is because any good representation will be able to classify color or grayscale domain. So by harming the representation to this extent, so essentially any good representation of a good neural network will actually be very discriminative with regard to a lot of things. And so harming it to not be discriminative inevitably harms it in more ways than one. So let me show you one other, basically option 2 for adversarial training, which is another sort of recent line of work. So here they said, instead of having a separate d-way softmax classifier, we're actually going to build a classifier on top, directly on top of the predictions. And then we're going to have a loss on the, again, classifier layer to make a good prediction. We're going to have a loss on the domain level to make a good domain prediction. And then the way we're going to propagate the gradient is essentially it's going to be the gradient of the classifier minus the gradient of the domain classifier. And this intuitively says, there's one more term we'll talk about in 1 second. And this intuitively says we're going to train the classifier to be able to predict the n classes, but we're going to reverse the gradient for the domain so that we can't predict the domain from seeing the classifier outputs. And there's also a projection term in there that sort of makes this more robust, and there's a mathematical argument for this. This, by the way, is the first paper that I showed that where they did some work and proved some guarantees with linear classifiers. So this sort of similarly gets, I mean, it's a different approach, but it gets a similar result. So one way to visualize this is, again, you can look through a t-SNE embedding for, so in the top you have the classifier, the features corresponding to different domains. So red is, I don't know, color, I think, and black is grayscale. And then right below that you have the object classes in different colors. And so you can see if there's no adversary, the object classes are sort of separable, but so are the domains. The domains also look kind of sort of the red and black kind of cluster together. As soon as you introduce an adversary, the adversary does a really good job of scrambling the domains, but it also does a really good job of scrambling the object classes in a way that's hard to recover. And one sort of final result to, yes? Go ahead.
Output of some layer?
Yeah, so this is the last, yeah, so, yeah, this is the last layer of the ResNet 18. Yeah. And so one sort of final result here is actually, so if you have a model that you've trained just on grayscale images, and you take the final layer and you try to classify an image as grayscale or color, that actually gets 95% accuracy. So clearly, even if you've just trained it without the domain at all, without having seen a single color image, it actually will still, the representation, just by virtue of being a good discriminative representation, will be good enough to classify color and grayscale. So clearly, this kind of adversarial approach is not going to work super well in kind of these kinds of more real-world scenarios, even though in theory you could see how it would. So we propose a couple of alternatives, so again, these are sort of very simple alternatives that you could imagine. So this is following the idea of sort of fairness through awareness, which is we're going to actually explicitly train different classifiers for each class and domain. So this is now a d-n-way classifier. So if you have 2 domains and 20 object classes, this is a 20-way softmax. And we're explicitly going to train it to predict each domain and class for image I. And then at test time, we actually have to do this prior shift adaptation. So we can do this through resampling, which does not work. But you can actually do this adaptation at inference time, which essentially says, look, at training time, the probability of this class Y and domain D was small, but we actually know that at test time is going to be uniform. So you can actually multiply and you can work through this derivation. I'm not going to work through it here, but it's basically 2 applications of Bayes' rule. But you could multiply the outputs of your, the net results, you multiply the outputs of your CNN by the ratio of expected probability of the domain D and the class Y at test time, which we assume to be uniform, so we can just think of that as 1, divided by the probability at training time. And this is a known application, although I don't think has been applied to fairness, but this is a known trick for adjusting for sort of doing domain adaptation of classifiers. And so with this, we get actually a much higher result than the baseline. So now we're starting to actually see sort of de-biased representations. And we try one last thing here, which is we call it a domain-independent model. So the domain-independent model essentially says, well, okay, but we're wasting model capacity classifying a grayscale ship from a color ship, even though at test time we're not actually going to care as much about this. We're sort of wasting model capacity. What if we have separate classifiers for the different domains? And in fact, perhaps even more importantly, it's not just that we're wasting model capacity, it's that we're not taking advantage of the fact that the classification boundaries between grayscale ships and grayscale cats will actually be similar to the classification boundary between color ships and color cats. So the classification boundaries between this, so in the domain discriminative model, we never take advantage of the fact that some of these classes are actually the same classes just across different domains. Whereas here we can say, we actually can explicitly take advantage of the fact that these are the same 10 classes just across the domains. And so we end up training 2 separate n-way softmax classifiers. Each one, so for each domain, it's just that they don't learn to discriminate between domains, they just learn to discriminate within the domain. And then at test time, we could actually sum their decision boundaries explicitly. So we don't sum their prediction, we actually sum explicitly the decision boundaries to get classification results. And so this does better than the domain discriminative model. What's interesting and troubling here is that this is actually still about 0.5% behind a model that would have been trained just on grayscale images. And that's something that we're still honestly grappling with and trying to figure out, like, we know that there is something the model can learn, which is literally take all of these images, conv one layer, like convert it all to grayscale, right? That's a straightforward, it's not even like straightforward linear operation, it can't be learned, right? So somehow we haven't yet figured out a way to enforce this in the model. So I mean, of course we can hard code it, right? But thinking more generally, we haven't quite figured out a way to enforce this. But as we're still struggling with this, so there's a few other settings and experiments that we've tried to sort of take this deeper, right? So this is on grayscale versus color and on CFAR and kind of in this simple domain. So we asked questions of, for example, sort of what happens when you have different skews of color grayscale in the data. So all of these experiments were done with 95.5% skew. Oh, sorry, I didn't actually put it up. So all of these experiments were done with 95.5% skew within the class. So that's the vertical line. But sort of what happens between the baseline and the domain independent model as the amount of skew gets smaller. And perhaps not surprisingly, as the amount of skew gets smaller, the amount that this sort of throws off your classifier gets smaller. And so the gap gets smaller and smaller and smaller. And actually, interestingly, you don't seem to observe this effect practically at all. It's very, very small when you get to sort of 75% skew. Not really sure what to do with that. In practice, a lot of real-world data lives at about 80%, so gender lives at about 80% average skew. So we've also tried looking at, for example, harder domains. So here we took CFAR examples still were one domain, but now the other domain, instead of being grayscale CFAR, we actually took color but ImageNet images for the same classes. So now the domain boundary becomes much harder to learn. So now this is not as trivial. This is a more complex domain. We see similar results with adversarial training, and then we see, again, sort of improvements in the domain-independent model, although it is actually, and this holds true in real-world settings as well, it actually becomes smaller as the difficulty of the domain classifier becomes bigger. We've also looked at more, sort of the simplest version of more and harder data, which is the Cynic 10 data set, which essentially is you take ImageNet images corresponding to the CFAR classes, you downsample them, and you sort of release that in the wild. This is like CFAR only, I think 5 times larger or so. So it's basic, and so we run the similar kind of experiment as on CFAR with color and grayscale, but now there's a lot more data. Here, oversampling actually performs worse, but again, this is, by the way, these are all hot off the press results. These are, in the last week, some of these, right? So especially this Cynic 10 was over last weekend, right? So this is very hot off the press. So oversampling here, we actually changed the protocol where we equalize the number of batches, and oversampling actually immediately dropped, but there's no reason to believe that as long as you equalize the number of epochs, it won't get up to baseline. What we observe here, interestingly, is that actually domain discriminative and domain independent end up being the same. And the hypothesis here is that, right, so before we said we want domain independent to be, we want domain independent so that we can combine their classification boundaries to do a better job. But here it seems like maybe there's just enough data of all of the different domains and of all of the different classes that we just don't need to do that. They sort of perform equivalently. And then I've sort of decided in the interest of time not to dive into the real world data, but we've run this on now 5 data sets. Again, all of this is sort of hot off the press. The Google spreadsheets are being filled in as I'm speaking here with sort of new results. But sort of Celeb A is a face recognition data set with gender attributes and a variety of other attributes. The goal is to classify the different attributes. They're correlated with gender. COCO is the standard object detection data set or object recognition, object classification data set. The appearance of different objects is also correlated with gender, so work has been done on that, and there's a variety of others. Here's a couple of takeaways that sort of emerge out of this. So first of all, in the real world, you get multi-label classification. So this requires formulating new metrics for evaluation. So this sort of idea of per class per domain accuracy actually no longer holds. You kind of have to think about things like weighted mean average precision, where now you sort of weight the different genders equally. You kind of have to think about like, what does it mean in this kind of data to decorrelate the two attributes and evaluate the predictions. There's one more thing I was going to say. You also have to think, right, so it turns out when you remove softmax and you now go to sigmoid loss, because now it's multi-label, this kind of prior shift arithmetic that I talked about, the test time inference for the discriminative model no longer holds, because now the probabilistic interpretation, the probabilistic interpretation of a softmax is already shaky. The probabilistic interpretation of a sigmoid is basically out the window. So doing any kind of prior shift on there just goes out the window. You just kind of have to accept it for what it is and either operate on domain boundaries or do other things. Then it seems like, so out of all of these experiments, there are kind of 3 key factors that are emerging that affect the kind of behavior that you would see. So one is the size of data set. We already sort of alluded to that with like Cynic versus CFAR, but the size of the data set changes a lot of things actually about the ordering of these models and what behavior you end up seeing. The skew of the data set, which again, we've already sort of hit upon, right? So when the skew is less, when the correlation between gender or whatever protected attribute and your classification is less, again, the model tends to not learn it as much. And related to that is the discriminativeness of the protected attribute. So how well can the model learn this gender? And so what we're working on now is actually trying to put together a sort of more comprehensive study across these different dimensions how do some of these conclusions or findings generalize? How do they hold under, like what are, these seem to be the three dimensions that matter and that affect results, but like in what way? And again, all of this is done with deep learning models, so this is not sort of abstract guarantees with sort of theoretical guarantees. This is like very practically, when we run this, what happens. But of course, this is now, you know, an exponential space. We need a lot of data sets. We need to make sure that things we're observing are not just idiosyncrasies of this particular data set, but there's sort of multiple data sets where we can support the claims. All right, so this is on the algorithm side, and there is, I mean, I think the biggest takeaway here, so again, all of this is very recent work, but I think the big takeaway is that there's many very interesting open questions kind of stemming from fairness considerations. And so before I conclude, if you give me 5 more minutes, I want to talk about one last thing in the fairness space, and so if we ask where's the social bias and can we mitigate it? So arguably the last bit of social bias comes from the people who are doing the research. Controversial statement, I know, and it is true that certainly a lot of this research can be done and is being done very effectively by people who don't necessarily come from the minority groups. However, there is inherent bias in these systems coming from just people deciding what problems are important, researchers deciding what problems are important to work on, researchers deciding where they care about collecting the data. So even if you try to be very broad in your data collection, the reality is the decisions that you make stem from your background and your set of values and your set of beliefs and so on. And so you have to believe that there is a significant amount of skew or bias in this whole research field that's sort of stemming from the fact that we as a community are not very representative of the world. And it's no surprise, right, that a lot of the bias results, right, so they're against people of certain racial demographics that are underrepresented in the community, they're against women who are underrepresented in the community. And so the last thing that I want to talk about again very briefly in a couple of minutes is the AI Furl Foundation, which is a foundation that I co-founded together with Feifei Li and with Rick Sommer back in 2016, where we say, look, AI will change the world. This is no question. The real question we ask is who will change AI and who will build this going forward. And so our mission very concretely is to increase diversity and inclusion in AI development policy and research. This is a foundation that's now it's based in California, has many full-time people employed there now to work directly on this problem. And there's 3 core initiatives and 3 core solutions that we propose. So we start at the high school level. So we start with, we're solving the pipeline problem. So the problem has to start with education. It has to start early on in the pipeline. By the time you get up to the grad school levels, there are things you can do, but the reality is you are too late. You've missed out on a lot of students. And so we do 3 core things. One is we start summer programs in collaboration with our partner universities. So we started the first summer camp at Stanford when I was a PhD student there. This was 2015. In 2017, we moved to we scaled to Berkeley. So 2016, we launched AI for All. 2017, we started a partner camp at Berkeley. In 2018, we were at 6 locations, and now in 2019, we're at 11 locations. Each of these camps picks a particular underrepresented group and designs a marketing strategy and a program around this group. So Stanford started out being for girls. Princeton, for example, is for underrepresented racial minorities. Berkeley is for local low-income students, and so forth. After that, so these are summer camps that are 1 to 3 weeks long. After that, AI for All creates the Changemakers in AI community, which is the community of our alums that have completed these summer programs. We provide them with internship opportunities, with mentoring, with opportunities to do their own outreach work, with social support, with sort of opportunities to meet locally with some of the other AI for All alums and so forth. And the last thing is we're launching the open learning education platform, both online and offline, expanding access to AI education. Because of course, these summer programs, it's a very intense intervention. It's usually about 20 to 32 students at each camp, and it's a 3-week program for those students that makes a lot of impact on them. But the reality is that it's still only 200 or so students per year so far. You can look at the statistics from the annual alumni survey in 2018. So how well did the students benefit from the summer camps, as well as are they going on to stay in AI? So 61% have, and these are, again, high school students who have many other things on their plate, but 61 of them have started AI or CS projects beyond the camp. 90% feel that they're part of a community in AI or computer science. 100% feel that AI can improve their world and their community, which is great, so no more killer robots. 87% feel that the AI field could benefit from their perspective. 77% are interested in a career in AI. 88% feel that they can succeed in AI. And 76% have participated in AI for all alumni events or programs. And this is my all-time favorite quote that I'll conclude on, that a student in 2016 said that until this program, I never thought that people who look like me could succeed in computer science and AI. And so if we're going to mitigate the social bias that we're building into the system, the technical work is going to be only part of the solution, and we actually need a diversity of representation among the AI developers to get there. Thank you. Happy to take questions.
Questions? So this was, the correlation with the domain was really extremely interesting, and but there are countless examples which we can really not predict. We cannot have a list of it.
Yes.
I remember Jack Gallop giving a talk once at CVTR, and giving us, like, I think, temples, and all temples were correlated with the blue sky. So
yep.
Everything that had a blue sky there was recognized as a temple. Even in social issues, there are things which we cannot be wasted. So how could we discover such correlations?
Yeah, I think that's a great question. The short answer is, first of all, there's a lot of problems already in the domains and then the correlations we know about. Second of all, I think this work has to be done in collaborations with social scientists, with people in the critical humanities, with people who are studying the different kinds of race and the different kind of bias and inequalities and social impact. And so this has to sort of be done in consortium with them, because they're the ones who are best equipped to discover the kind of factors that might matter or that we should be aware of, and then it's our job to fix them.
Other questions?
I have a question about, on the last slide,
Mm-hmm.
when you talk about AI for all,
Mm-hmm.
when you're talking about open education, so there are a lot of platforms right now that offer free classes and things like that online. So what is it that you guys are doing that is different from your policy?
So great question, and several. So I'm one of the board members at AFL, and we ask this question of the team all the time: is sort of how are we going to differentiate? So several things. So one is we do both online and offline. Two is we're very focused on social impact of the work. So there's a lot of studies that say that, in particular, women tend to be more motivated by applications that have a social impact, and so everything we teach both at the summer camps as well as in the open learning is motivated by this idea of sort of AI as positive, social, good, transformative technology. And so all of the examples, so it's not just, you go in and you're going to learn, deep learning because deep learning is cool. No, you're going to think through through a curriculum that's developed by an expert working in a particular sort of social change area. You're going to think with them, sort of work through the technology that it would take to make that kind of social change happen. But this is very new. So this was launched. The pilots are launched in early 2019, right? So we just launched the very beginnings of this.
I have a question about the speaker that we have here. So you said that both better training data and better algorithms could help in this problem. Which one would you say is more important? And I'm asking that, for example, if we want to have some AI system that will be used in a criminal justice.
Yes.
Then we should tell the government that they should pay to get better, legal data for what we want, right? And they should spend all their money on that.
I think there's no amount of effort that will be too much. I think whatever effort you can contribute and are willing to contribute, I think would be great. I think we're very far from solving this from either side. I think we'll need effort on both fronts. So I guess even, so you